there is a particular kind of darkness that most people have never experienced. Not the darkness of a room with the lights off, not the darkness of a cloudy night. Something far deeper. Something that has no name in ordinary language, because ordinary human experience has never required one. Astronomers call it the void between galaxies, regions of space so empty that light itself becomes a stranger there, traveling for millions of years without encountering a single atom to illuminate. If you were placed at the center of such a void, you would look in every direction and find nothing. No star, no cloud of gas, no dim smudge of a distant galaxy on the horizon, just an absolute, perfect, impenetrable blackness stretching outward forever. Most of us assume we will never experience that kind of darkness. We live in a galaxy filled with over 300 billion stars, spinning through space like an enormous pinwheel of fire and gravity and ancient light. The Milky Way has been burning since before the Earth existed, before the sun was born, before the first amino acids assembled themselves into the first stirrings of life anywhere on this planet. It has been here, and it has been bright, and it has been the engine of almost everything we are. But what if it wasn't? What if, in some strange hypothetical moment, every single star in the Milky Way simply ceased to exist? Not dimmed, not faded, not slowly burned out over billions of years the way stars normally do. Just gone. All 300 billion of them vanished in an instant. The question might sound like science fiction, and in a sense, it is. Nothing in known physics allows for such an event. But that is precisely why it is worth asking, because answering what would happen if every star disappeared requires understanding what stars actually do. Not just the obvious things like producing light and warmth, but the deeper things, the invisible things, the things that most people never consider because stars have always been there, quietly performing their roles. And no one has ever had any reason to ask what would remain if they didn't. What stars do turns out to be extraordinary, and what would be lost without them turns out to be almost everything. This is a journey into that darkness, a journey that begins with an impossible event and follows its consequences outward through time. From the first second after the stars vanish, through the years and centuries and millennia that follow, into a future that grows stranger and more alien with every step. By the end, you will see the Milky Way differently than you do now, because understanding what would be destroyed reveals, more clearly than almost anything else, just how remarkable the ordinary night sky really is. Let's begin at the moment it happens. The stars are gone. Not fading, not exploding, just gone, as though 300 billion suns simply stepped out of existence between one instant and the next. The first thing to understand is that you would not know immediately. This seems counterintuitive. Surely the disappearance of every star would be instantly obvious, but here is the strange truth about how we perceive the universe. We don't see what is happening right now. We see what was happening when the light that just reached our eyes originally left its source. The Sun, our nearest star, is about 8 light minutes from Earth. That means the light currently illuminating the surface of this planet left the Sun 8 minutes ago. If the Sun vanished right now, in this hypothetical instant, Earth would continue receiving sunlight for 8 more minutes. The sky would remain blue. The ocean would remain warm. The shadows would remain exactly where they are. And then, after 8 minutes, without any warning, the light would simply stop. But the Sun is our closest star, For every other star in the Milky Way, the delay is far longer. Proxima Centauri, the nearest stellar neighbor, is 4 light-years away. Its light would continue arriving for 4 years after it vanished. The stars of the Orion constellation, which most people recognize, are hundreds of light-years away. Their light would continue reaching us for hundreds of years. Some of the stars visible on a clear night are thousands of light-years distant. Their light, already ancient, would continue arriving long after the stars themselves had ceased to exist. In the first moments after the stars vanish, then, the sky would look completely normal. This is one of the most unsettling aspects of this hypothetical. There would be no warning, no announcement. The universe would appear, to any observer anywhere in the galaxy, to be exactly as it always was, for a while. But that appearance would be a kind of cosmic illusion, an after-image. The stars would be gone, but their ancient light would still be traveling across the galaxy, still arriving at destinations that the stars themselves would never illuminate again. The delay between the event and the perception of it would vary depending on where you were standing and which direction you were looking. An observer on Earth would lose the sun's light after 8 minutes. The star that used to shine in the night sky 4 light-years away would vanish from view 4 years later. The most distant stars in the Milky Way, tens of thousands of light-years from Earth, would continue shining in the night sky for tens of thousands of years, even though they no longer existed. Imagine living through that. Imagine looking up at a night sky full of stars, knowing they were already gone, knowing that the light arriving in your eyes began its journey before any of those stars ceased to be, and that you were watching a kind of beautiful cosmic lie. A sky built entirely from the past, offering no clue about the present. This is not a small philosophical point. It matters enormously for understanding what would follow, because the consequences of losing every star would not arrive all at once. They would arrive in layers, separated by time, each one more profound than the last. To understand those consequences, it helps to understand what stars actually are, not just physically, but in terms of their role in the larger galaxy. Most people, when they think of stars, think of light and heat, and that is correct, but it is only the beginning. Stars are, in a very real sense, the engines of the galaxy. They drive almost every process that makes the Milky Way what it is. And the way they do this is far stranger and more intimate than most people realize. Start with something fundamental. Gravity. A star is not just a ball of burning gas. A star is an enormous gravitational object. The Sun, for instance, contains more than 99% of all the mass in the solar system. Everything else, all 8 planets, all the moons, all the asteroids and comets and rings and dust, constitutes less than 1%. The Sun's gravity is what holds all of it together. It is the invisible architecture upon which the entire solar system is constructed. And this is true for every star in the Milky Way. Every planetary system in the galaxy is held together by the gravity of its host star. Every orbit is maintained by that gravity. Every moon that circles a planet does so because of a chain of gravitational relationships that ultimately traces back to a star. Without stars, all of those gravitational anchors disappear simultaneously. What happens to a planet when its star vanishes? The planet keeps moving. That is the crucial point. A planet in orbit around a star is not stationary. It is moving at tremendous speed, constantly being pulled toward the star and constantly curving away from it, tracing an endless ellipse through space. This balance of motion and gravity is what an orbit is. Remove the gravity and the motion remains. The planet, now free from the gravitational pull that was curving its path, continues in the direction it was traveling at the moment the star disappeared. It does not fall somewhere. It does not stop. It simply keeps going in a straight line at whatever speed it had, moving away from where its star used to be, heading out into the wider galaxy. Earth, in this moment, would be doing exactly that. Moving at roughly 30 kilometers per second relative to the Sun, it would continue traveling in the direction it was pointing when the Sun vanished. The Moon would detach from Earth's gravity within a different calculation entirely. Actually, it would not immediately, because the Earth still has its own mass and gravity, and the Moon would remain in orbit around the Earth. But Earth itself, now a rogue planet, would drift away from where the Sun had been, carrying its Moon with it, moving silently through an increasingly cold and dark galaxy. Every planet in every solar system in the Milky Way would do the same thing. Hundreds of billions of planets suddenly cut loose from their gravitational anchors, spreading outward through the galaxy like seeds scattered from a dying plant. The galaxy would not explode. It would not collapse. It would become something strange and quiet and deeply unfamiliar. A vast space filled with cold, dark, drifting worlds and the remnants of what used to be planetary systems. But the loss of gravity is only one consequence. There is something else that stars provide, something that may be even more fundamental. And it concerns a concept that most people take entirely for granted. Energy, not just the energy of light and heat. Something more profound than that. The universe, at its most basic level, is governed by thermodynamics, the laws that describe how energy moves. One of those laws is simple but unavoidable. Energy always flows from hotter regions to colder ones. Heat does not move from cold to warm. It moves from warm to cold, always. Stars are the warmth. Space is the cold. The temperature of deep space, far from any star, is approximately 2.7 degrees above absolute zero. This is not a number that most people have any intuitive sense of. Absolute zero is the point at which all molecular motion ceases entirely. It is the coldest anything can possibly be. And deep space is almost there, almost at the coldest point the universe permits. Stars push back against this coldness. They pour energy into the space around them, warming the objects nearby, driving the temperature of local environments far above the universal baseline. Without stars, everything eventually falls toward that baseline. Everything drifts toward 2.7 Kelvin. On Earth, this process would begin the moment the sun's light stopped arriving. The first hours would be deceptively normal. The atmosphere holds heat extremely well. It is an insulating blanket wrapped around the planet, and it does not lose its warmth instantly. The oceans, even more so. They contain an enormous amount of thermal energy, accumulated over billions of years of sunlight, and they would not surrender that energy quickly. But the temperature would fall, consistently, relentlessly. Within a week, average surface temperatures on Earth would drop to around -15 degrees Celsius in most places. Within a year, they would approach -50. Within decades, they would approach -100, and still falling, because there would be nothing to stop the loss of heat to the surrounding void. Glaciers would expand and eventually merge. Oceans would freeze from the surface downward, slowly but inevitably. The atmosphere itself, given enough time, would begin to condense. The nitrogen and oxygen that make up the air we breathe would eventually become liquid, and then solid, settling onto the frozen surface like a layer of crystalline snow. And this is not just Earth. This is every planet in the galaxy that ever received warmth from a star. The transition from a galaxy of illuminated, warmed worlds to a galaxy of frozen, dark ones would take thousands of years in full. Some worlds cooling faster than others, depending on their distance from their stars, their atmospheric composition, their internal geology. But the direction would be the same everywhere. Everything drifting toward the cold. Everything surrendering its borrowed warmth back to the void. There is, however, one source of heat that does not come from stars: the interior of a planet. Earth has a molten iron core, and it has had one for billions of years. This internal heat comes from two sources. The original heat of formation, when the planet coalesced from a disk of spinning gas and rock 4.5 billion years ago, and the ongoing decay of radioactive elements deep in the planet's interior. Both of these heat sources are independent of the sun. They do not require starlight. They exist entirely within the planet itself. This means that even after the surface froze, even after the oceans solidified and the atmosphere collapsed, and the sky went permanently dark, the deep interior of the Earth would remain warm. Not warm enough for the surface to feel any of it. The insulating depth of rock is too great, but warm enough that liquid water might persist in pockets, deep within the crust. Warm enough that the geological engine of plate tectonics might continue operating for hundreds of millions of years, slowly moving the frozen rock of the surface, still building mountains and filling valleys, still reshaping a world that no one was left to see. And this is a clue to something important, because life, as it turns out, does not always require starlight. Deep in the ocean trenches, in the complete darkness of the seafloor, where no sunlight has ever reached, there are ecosystems built around hydrothermal vents, cracks in the ocean floor, where superheated water erupts from the Earth's interior, carrying minerals and chemical energy from below. These ecosystems are not powered by photosynthesis. They are powered by chemistry, by the heat of the Earth itself, by the energy of radioactive decay happening deep in the rock. In a galaxy without stars, those vent communities would be, for a while, the last places where liquid water persisted, the last places where temperature gradients, strong enough to drive chemistry, still existed. The oceans above them would freeze. The surface of the planet would be unrecognizable. But deep beneath the ice, where the heat from the core still reached, water might remain liquid for millions of years. Whether that is enough for life to persist is an extraordinary question, but the possibility exists. Quietly, hidden beneath miles of ice, in the darkness at the bottom of a frozen ocean, on a world drifting through a galaxy that no longer had any stars. The universe has a way of finding corners where life might hide. But let's step back from individual planets and consider the Milky Way as a whole. The galaxy is not just stars and planets. It is also gas and dust, enormous clouds of hydrogen and helium and heavier elements that drift between the stars, forming what astronomers call the interstellar medium. This material is the raw ingredient from which stars form. It is also shaped, compressed, heated, ionized, and stirred by the stars themselves. Stars are not passive objects sitting in an empty galaxy. They are active participants in the structure and behavior of the galaxy around them. Consider what stars do to the gas that surrounds them. Young, massive stars are extraordinarily energetic. They emit enormous quantities of ultraviolet radiation, a form of light invisible to human eyes but powerful enough to strip electrons from hydrogen atoms, converting neutral gas into what physicists call plasma. This process, called ionization, creates vast glowing regions around young stars called HII regions, some of which are large enough to contain entire solar systems within their boundaries. These regions are among the most visually dramatic objects in the galaxy. Great nebulae of color and light, where the energy of young stars is carving and sculpting the gas around them into pillars and arches and shells. Without stars, all of this stops. The ionized gas would gradually recombine, electrons finding their way back to the protons they had been separated from, the plasma cooling and neutralizing, and becoming ordinary hydrogen gas again. The great glowing nebulae would go dark. Not instantly, but within thousands of years. An eye blink in astronomical time. The galaxy's most spectacular visual features would fade. But that is almost a cosmetic consequence compared to what else the stars do to the interstellar medium. Massive stars, at the end of their lives, explode. These explosions are called supernovae, and they are among the most energetic events in the known universe. A single supernova releases more energy in a few seconds than the Sun will emit over its entire 10 billion year life. The shockwave from a supernova expands outward through the surrounding gas at thousands of kilometers per second, compressing it, heating it, accelerating it, mixing it, and stirring the interstellar medium in ways that shape the formation of the next generation of stars. Supernovae are, in this sense, the heartbeat of the galaxy. They are the mechanism by which the interstellar medium is continuously recycled, compressed and heated and mixed, so that new stars can form from the enriched material left behind. Without supernovae, the gas between the stars would slowly lose its structure. The turbulence that helps stars form would decay. The galaxy's star-forming regions would grow cold and quiet, and without new stars being born, the galaxy would have no way to replenish what it loses. This brings us to something that most people have never thought about: where the atoms in your body came from. You are made of hydrogen, carbon, oxygen, nitrogen, and dozens of other elements. The hydrogen in the water molecules in your cells is as old as the universe itself. It was forged in the first 3 minutes after the Big Bang, when the universe was hot enough for protons and neutrons to fuse. But almost everything else in your body, the carbon in your DNA, the oxygen in your lungs, the calcium in your bones, the iron in your blood, was made inside a star. Not metaphorically, literally. Stars are nuclear reactors. In their cores, where temperatures reach tens of millions of degrees and pressures are almost unimaginable, hydrogen atoms fuse together to form helium, releasing energy in the process. That is what stellar fusion is: the conversion of one element into another, with a release of energy that powers the star. But in larger stars, this process goes further. When the hydrogen runs out, the star begins fusing helium into carbon and oxygen. When that runs out, it begins fusing those into heavier elements: neon, magnesium, silicon, sulfur. And at the very end, in the most massive stars, the fusion chain reaches iron. Iron is the graveyard of stellar fusion. It takes more energy to fuse iron than the process releases. When a star's core becomes iron, the fusion stops. The core collapses. The star explodes in a supernova. And in that supernova explosion, the elements built up over the star's lifetime, plus all the heavy elements created in the explosion itself, elements heavier than iron that can only form in such extreme conditions, are scattered outward through space. They mix with the interstellar medium. They eventually become part of new clouds of gas. And those clouds, given time and the right conditions, collapse into new stars and new planets. The Earth is made of material that was ejected from dying stars. You are made of material that was ejected from dying stars. Every carbon atom in every living thing on this planet was forged in a stellar core and scattered by a supernova, possibly billions years before the Sun was born. Carl Sagan famously said that we are made of star stuff. He was not speaking poetically, he was speaking chemically. In a galaxy without stars, this cycle stops completely. No new fusion, no new elements heavier than hydrogen being created anywhere. No new supernovae to scatter those elements through space. The existing atoms remain. All the carbon and oxygen and iron and gold that was ever made would still be out there, on the dark frozen worlds, drifting through the starless galaxy, but nothing new would be added. The periodic table, for practical purposes, would be closed. This matters for an almost philosophical reason. The emergence of complexity in the universe, the progression from simple hydrogen and helium to the astonishing variety of chemistry that makes planets and oceans and life possible, depended entirely on stars. Stars were the factories where simple atoms were transmuted into complex ones. Without them, chemistry would freeze at its most basic level. A galaxy without stars would be a galaxy where the universe's experiment in complexity had reached its limit and stopped. There is another thing that stars provide, something more subtle than light or gravity or nuclear fusion, that almost never gets discussed. Protection. The Milky Way is embedded in a larger environment. The local group, the collection of galaxies that includes the Milky Way, Andromeda, and dozens of smaller satellite galaxies, is itself embedded in the larger cosmic web, the vast filamentary structure of matter that spans the observable universe. And flowing through this structure in all directions is a constant stream of high-energy particles. Cosmic rays. Cosmic rays are not rays in the traditional sense. They are particles, protons, helium nuclei, and occasional fragments of heavier atoms traveling at nearly the speed of light. They originate from supernova remnants, from the environments around black holes, from events in other galaxies. They are extraordinarily energetic, and they are constantly raining down on everything in the universe. On Earth, we are largely protected from cosmic rays by two things: the Sun and the Earth's magnetic field. The Sun, as part of its constant activity, generates what is called the solar wind, a continuous flow of charged particles streaming outward from its surface in all directions. This solar wind creates a magnetic bubble around the solar system called the heliosphere, which extends far beyond the orbit of Pluto. The heliosphere acts as a partial shield against the most energetic cosmic rays, deflecting and attenuating them before they reach the inner solar system. Closer to Earth, our planet's own magnetic field provides additional protection, generated by the motion of liquid iron in the outer core. Earth's magnetic field creates another bubble, the magnetosphere, that deflects charged particles that manage to penetrate the heliosphere. These protections are not perfect. Some cosmic rays reach the surface, but without them, the intensity of radiation at Earth's surface would be dramatically higher. Remove the Sun, and the heliosphere collapses. the solar wind stops. The magnetic bubble that has been protecting the inner solar system for billions of years simply ceases to be maintained. The outer solar system would be the first to experience the full intensity of cosmic rays from the wider galaxy. Over time, as Earth drifted away from where the Sun had been, it would lose even the residual protection of the heliosphere. The planet still has its own magnetic field generated from within, but without the Sun's complementary protection, the environment at the surface would become significantly more hostile to complex organic chemistry. This is a reminder that stars are not isolated objects. They are participants in a web of relationships that extend across entire planetary systems. And in the case of the galaxy's most massive stars, across entire star-forming regions spanning hundreds of light years. We should talk about what the galaxy would look like from the inside in the centuries after the stars disappeared. Imagine standing on a world in the outer reaches of the Milky Way, a few thousand years after the event. You look up. What do you see? In one direction, the direction toward the center of the galaxy, you might still see light. The center of the Milky Way is about 26,000 light years from Earth. Light from the stars that used to burn there is still traveling, still arriving at your position. Thousands of years after the stars vanished, their light would still be in transit. You would look toward the galactic center and see a faint, warm glow. The afterimage of billions of dead stars, their light still crossing the void between where they were and where you are. In the other directions, closer regions of the galaxy would have already gone dark. The stars that used to be nearby would have winked out years or decades ago. Depending on their distance, you would find yourself in a peculiar position, surrounded by darkness in most directions, but with one hemisphere of the sky still faintly illuminated by light arriving from stars thousands of light years away that no longer existed. This would change over centuries. The light would continue arriving from ever more distant parts of the galaxy. But the sphere of illumination would shrink rather than grow. As the light from nearer stars was exhausted, newer light arrived from farther ones, but there would be progressively less of it, spread across a progressively larger sphere. The galaxy would dim, slowly at first, and then more quickly, until after perhaps 50 or 60,000 years, approximately the diameter of the Milky Way in light years, the last light from the last stars would arrive, and then there would be nothing. Perfect darkness across the entire galaxy. Except for one thing. The galaxy's black holes would still be there. The Milky Way contains a supermassive black hole at its center. It is called Sagittarius A, and it contains the mass of approximately 4 million suns compressed into a region smaller than our solar system. It is not currently particularly active. It is not consuming large quantities of matter, not generating powerful jets of energy. By the standards of the supermassive black holes found at the centers of other galaxies, it is relatively quiet. But it is there, and it is not going anywhere. Black holes are not powered by the same processes as stars. They do not require fusion. They do not depend on the nuclear reactions that generate stellar energy. A black hole is simply a region of space where gravity is so extreme that not even light can escape. It persists because mass persists. It cannot be burned away or consumed the way a star's fuel can be. In a galaxy without stars, the black holes would remain, and if they had any matter falling into them, gas, dust, drifting planets wandering too close, they would continue to release energy. This energy comes not from within the black hole, but from the material approaching it. As matter falls toward a black hole, it heats up. Friction and compression drive the temperature to extraordinary levels, causing the infalling material to glow in active galactic nuclei. Galaxies where the central black hole is consuming large quantities of matter. This process generates more light than the combined output of hundreds of billions of stars. Sagittarius A is not currently in this state. It is too quiet, too starved of material, but in a starless galaxy, where drifting planets and gas clouds were gradually being pulled inward by the black hole's gravity over millions of years, the situation might eventually change. The slow accumulation of material might eventually trigger renewed activity. Brief flares of intense radiation from the galactic center blazing out across a dark galaxy with no stars to compete with their light. In a galaxy of perfect darkness, a feeding black hole might be the only light. Let's take a wider view. The Milky Way does not exist in isolation. It is part of the local group. And beyond the local group, it is embedded in the larger cosmic structure that extends across billions of light years in every direction. The Andromeda Galaxy, the Milky Way's nearest large neighbor, is approximately 2.5 million light-years away. Light from Andromeda takes 2.5 million years to reach us. If every star in the Milky Way vanished today, observers in Andromeda would not notice for 2.5 million years. They would continue seeing our galaxy exactly as it is now. A bright spiral of hundreds of billions of stars glowing across the void. For 2.5 million years before the light cutoff reached them. And conversely, if we were looking at Andromeda from a dark and starless Milky Way, the Andromeda Galaxy would continue appearing normal for 2.5 million years. Its stars still burning, completely unaffected by our hypothetical, would send their light across the void, and that light would reach our starless galaxy. From the surface of a frozen, dark Earth drifting through the void, an observer with a clear enough atmosphere would be able to look up and see the faint smudge of Andromeda, the most distant object visible to the naked eye. That smudge would be proof that stars still existed, just not here. It would be a strange and haunting thing to contemplate. The nearest galaxy, normal and bright and full of living stars, completely unaware that anything had changed. And here in the darkness, the remnants of a civilization that had once looked up at its own galaxy and marveled at the stars. The universe beyond the Milky Way would not change. The cosmic web of filaments and voids and galaxy clusters that spans billions of light years would continue exactly as before. The cosmic microwave background, the faint afterglow of the Big Bang itself, the oldest light in the universe, would continue washing over everything at the same intensity. The laws of physics would remain exactly what they have always been. Only the Milky Way would be different. Only here would the machinery have stopped. Now, we need to talk about something that people rarely connect to stars, but which is, in a sense, the most profound consequence of their disappearance. Time. Not the passage of time. Time would continue implacably, regardless of what happened to the stars. But the measurement of time, the calibration of it, the way in which time and the universe are linked for any civilization that might someday look up and try to understand where they are and when they are. Stars have been clocks since long before humans evolved to look at them. The rotation of the Earth relative to the Sun defines the day. The orbit of the Earth around the Sun defines the year. The precession of Earth's axis driven in part by the gravitational pull of the sun and moon, defines cycles of thousands of years. The positions of stars in the night sky, slowly shifting over centuries due to the combined effects of stellar motion and Earth's own orbital evolution, provided ancient navigators with both direction and a calendar. Without stars, all of this collapses. There would be no day and night. The rotation of the Earth would continue, but with no sun to mark the difference between light and dark, the distinction would cease to exist in any meaningful sense. There would be no year. The orbit itself would be broken by the sun's disappearance, and Earth would no longer be circling anything. There would be nothing in the sky to navigate by, nothing to calibrate a calendar against, nothing external at all. This is a subtler loss than heat or light, but it is a real one. Stars do not just illuminate the sky, they provide structure to experience. They are the reference points against which events are measured, the fixed background against which change becomes visible. The ancient Egyptians oriented their pyramids by the stars. Polynesian navigators crossed the Pacific by the stars. Every calendar in human history has been anchored to stellar or solar cycles. In a galaxy without stars, all of that context vanishes. The universe becomes, in a deep sense, undateable. There are no longer any natural cycles to count. There is no longer any external rhythm to mark the passage of time. But let's consider something even more unexpected. What would happen to the structure of the Milky Way itself? The galaxy's visible stars, the ones we can see and study, are not the majority of its mass. Far from it. Approximately 85% of the Milky Way's mass is invisible. It does not emit light. It does not absorb light. It cannot be detected by any telescope currently in existence. It is called dark matter, and it is one of the deepest mysteries in modern astrophysics. We know dark matter exists because of the way the galaxy moves. Stars in the outer regions of the Milky Way orbit the galactic center at speeds that should not be possible given only the visible mass of the galaxy. By the laws of gravity, stars farther from the center should orbit more slowly, just as the outer planets of the solar system orbit the sun more slowly than the inner ones. But they don't. They orbit at roughly the same speed as stars, much closer to the center. The only explanation that currently fits the observations is that there is additional invisible mass distributed throughout and around the galaxy. Mass that provides gravitational pull without emitting light. This dark matter halo extends far beyond the visible boundaries of the galaxy, wrapping it in an enormous gravitational cocoon. When the stars disappear, the dark matter remains. Dark matter, as far as we can tell, does not interact with normal matter in any way except through gravity. It does not burn. It does not fuse. It does not produce light. It is simply there, contributing its enormous mass to the gravitational structure of the galaxy. This means that, even without a single star, the Milky Way's gravitational skeleton would persist. The dark matter halo would continue holding the galaxy's shape, or at least the shape defined by dark matter distribution. The drifting planets, the cold clouds of gas, the neutron stars and stellar remnants, all of the remaining debris of the galaxy's stellar population would continue orbiting in a galaxy whose gravitational structure was still fundamentally intact. The galaxy would not fly apart. It would continue, in some sense, as a gravitational entity, a vast, dark, cold, invisible structure shaped by mass that no one can see and orbited by matter that produces no light. This is deeply strange to think about. most of what makes the Milky Way what it is. In terms of mass, in terms of gravitational architecture, in terms of the large-scale structure of space in this region, would survive the disappearance of the stars. The stars, for all their brilliance, for all their energy, for all their importance to every planet and moon and potential biosphere in the galaxy, would turn out to be a relatively minor fraction of the Milky Way's total content. The galaxy would go dark. But in a profound physical sense, most of it would still be there. Let's return to the planets. In the centuries and millennia after the stars disappear, the billions of worlds that used to orbit those stars would be drifting through the dark galaxy in essentially random directions. The directions they happen to be moving at the moment. Their gravitational anchors vanished. Most of them would never encounter anything. Space is so vast, and the objects in it so small that even a galaxy full of drifting worlds would rarely produce collisions or close encounters. The planets would simply drift, cold and dark, moving through the void at whatever speed they had when their stars disappeared. But occasionally, very occasionally, over the vast timescales of millions and billions of years, two of these rogue planets would pass near enough to each other for their gravity to matter. The encounter would be brief and, most of the time, would simply deflect both planets onto slightly different courses. But in rare cases, a closer encounter might allow one planet to capture another, creating a system of two rogue worlds orbiting each other, exchanging tidal heat, possibly even maintaining liquid water in some extreme subsurface environment from the tidal flexing generated by their mutual gravity. This is not entirely speculative. We already know that rogue planets, worlds ejected from their solar systems by gravitational interactions with other planets, exist in the galaxy in significant numbers. Some estimates suggest there may be more rogue planets in the Milky Way than there are stars. These worlds are cold and dark on the surface, but some of them may harbor liquid water beneath thick ice layers, maintained by tidal heating or radioactive decay in their cores. In a starless galaxy, rogue planets would be the dominant form of planet, not orbiting stars, simply drifting. And if any of them retained liquid water in hidden subsurface oceans, the possibility of life, very alien, very different from anything we know, sustained by chemistry and geothermal energy rather than sunlight, could not be entirely ruled out. The universe, it seems, does not give up on complexity easily. There is one more thing to discuss in this first part of our journey, and it is perhaps the most philosophically significant consequence of all. The loss of every star in the Milky Way would not just be the loss of light and heat and the nuclear engines that forge elements. It would be the loss of a particular kind of possibility. Stars are time machines in a sense. When we look at a star, we are not seeing it as it is now. We are seeing it as it was when the light we are currently observing left it. The sun we see is 8 minutes old. The nearby stars, visible to the naked eye, are years to decades old. The distant stars in the Milky Way are thousands of years old. Looking outward across the galaxy is looking backward through time. This means that the night sky is not a static picture. It is a living archive, a record of the galaxy's past, written in light, available for any civilization with eyes to read. Every star we see is a message from a different moment in the past, a direct line of communication across time. Astronomy is, in its deepest form, the science of reading those messages and reconstructing from them a history of the universe. Without stars, that archive is closed. There are no more messages, no new light arriving from the past to be decoded. The record falls silent, and the universe becomes, in a sense, unreadable. We often think of what we would lose in purely physical terms: warmth, light, energy. And those losses are real and enormous. But there is this other loss too, the loss of legibility, the loss of the universe's ability to communicate with itself across time, through the light of its own stars. The Milky Way has spent 13 billion years building this archive. Every star that ever burned left its light spreading outward at the speed of light. A permanent record of its existence, encoded in the most fundamental carrier of information the universe has. That record would continue spreading. The light from all the stars that ever existed in this galaxy would continue outward into the wider universe, long after the galaxy itself had gone dark. In billions of years, that light would reach distant galaxies, carrying the story of a galaxy that once burned brightly. But from within the Milky Way, the archive would have closed. The messages would all have already arrived. There would be nothing new. The question that keeps pulling us forward is not just about what would be lost. It is about what would remain, because something remarkable would remain. The dark matter, the cold clouds of gas, still rich with carbon and oxygen and iron and every heavy element ever forged in a stellar core. The neutron stars and white dwarfs, the dense remnants of stellar cores that had already burned out before the event. The supermassive black hole at the galactic center, patient and enormous, still shaping space with its gravity. And the planets, billions of them, drifting through the cold dark, some of them possibly still warm enough inside for chemistry to happen. The raw ingredients of everything would remain. The information, encoded in the physics of those materials, in the quantum states of every atom, in the gravitational relationships between every object, would remain. What would be missing is the energy to drive it, the engine. Stars were the engine. Without them, the galaxy would not cease to exist. It would become dormant, cold, patient, like a machine switched off, all the parts still present, all the connections still intact, waiting for something that might never come. In a universe that will continue for trillions upon trillions of years, the question of what might eventually drive that engine again, under what circumstances, through what process, over what timescales, becomes one of the most fascinating questions one can ask. And it turns out the universe has some ideas. Before we go deeper into consequences, it is worth pausing to think about something that is easy to miss in a thought experiment like this: the sheer scale of what we are discussing. Most people, when they try to imagine the Milky Way, picture something like the photographs they have seen. A pale band of light stretching across a dark sky, or an artist's rendering of a spiral galaxy viewed from above, glowing with billions of points of light arranged in elegant arms of gas and stars. Neither image quite captures the reality. The Milky Way is approximately 100,000 light-years in diameter. That number deserves to sit for a moment. 1 light-year is the distance light travels in a year, about 9.46 trillion kilometers. 100,000 of those, laid end to end, is a number so large it effectively has no meaning in human experience. If you could travel at the speed of light, it would still take you 100,000 years to cross the galaxy from one edge to the other, at the speed of the fastest spacecraft humanity has ever launched. Voyager 1, the most distant human-made object, which has been traveling for nearly 50 years. It would take approximately 1.7 billion years to cross the Milky Way. This is the space into which we are imagining every star vanishing. And within that space, there are structures of enormous variety and complexity. The galactic center, where the density of stars is so high that from a planet there, the night sky would never truly be dark. The spiral arms, where young blue-white stars and stellar nurseries are concentrated. The galactic halo, an extended region above and below the plane of the galaxy, where older, dimmer stars orbit in long, elliptical paths that carry them far from the galactic disk. The satellite galaxies, the large and small Magellanic Clouds, and dozens of smaller dwarf galaxies, orbiting the Milky Way at various distances, some of them in the process of being slowly disrupted and absorbed. All of these structures would be affected differently and on different timescales by the disappearance of every star. In the galactic center, where stars are densely packed, the loss of so many gravitational anchors in such a small volume of space would create significant gravitational disruption. Planetary systems that had been orbiting in relatively stable configurations would find those configurations immediately perturbed by the simultaneous loss of the gravitational field of their host star. The high stellar density would mean that some planets, in the moments after their stars disappeared, would find themselves relatively close to other planet populations, close enough, in astronomical terms, for gravitational interactions to occur over relatively short timescales. In the outer arms of the galaxy, the situation would be different. Stars there are more widely separated, tens of light years between neighbors, rather than fractions of a light year, as in the galactic center. Planets drifting loose from their stars in the outer arms would have vast distances to cross before encountering any other matter. They would move through an emptiness that would feel, even by the standards of space, extraordinary. And in the satellite galaxies, still gravitationally bound to the Milky Way, their own stars presumably unaffected by this hypothetical, the event would not be directly felt at all. The dwarf galaxies would continue orbiting the now dark mass of the Milky Way, following the gravitational field generated by its dark matter halo, indifferent to the fact that the galaxy they were orbiting was no longer emitting any light. From the surface of a planet in the large Magellanic Cloud, looking toward the Milky Way, you would see a strange sight. Where once there had been a faint spiral of light stretching across a portion of the sky, the external view of our galaxy, a smudge that is faintly visible even from Earth on the clearest nights, there would be nothing. No glow, no spiral arms, no central bulge, just darkness. The Milky Way, from the outside, would have simply disappeared. We talked about what stellar nucleosynthesis means for the creation of heavy elements. But there is a more intimate dimension to this story that deserves its own space. The carbon atom in a molecule of DNA, in the nucleus of a cell in your body, has a history. It is not a piece of information anyone can recover. The specifics are irrecoverable, buried too deep in time and chance. But the broad outlines of that history are known with confidence. That carbon atom was forged inside a star, not our sun. The sun does not produce carbon in significant quantities. It is a relatively small star, and its fusion chain is not energetic enough to build carbon efficiently. That carbon was made in a larger, heavier star, billions of years ago, somewhere in the galaxy. It was forged in a process called the triple alpha process, in which 3 helium nuclei fuse together to form a carbon nucleus under conditions of extreme temperature and pressure found only in stellar interiors. When that star ran out of fuel and died, either in a gentle puff as a red giant shedding its outer layers, or in a catastrophic supernova explosion, that carbon atom was released into space. It became part of the interstellar medium, drifting for millions or perhaps billions of years in a cloud of gas and dust. Eventually, that cloud, under the influence of gravity, began to collapse. It fragmented and condensed, and from its collapse emerged new stars, and around at least one of those stars, new planets. One of those planets was Earth. On Earth, over billions of years, geological and chemical processes concentrated and rearranged atoms. Life emerged. Atoms were incorporated into organic molecules, passed through generation after generation of organisms, shuffled and reshuffled through the biochemical processes of digestion and growth and death and decomposition. And at some point in the last century or so, some specific arrangement of biological processes brought that ancient carbon atom, that relic of a star that died before the Earth existed, into the body of a human being. Every person alive today carries within them atoms that have been on this journey. Atoms older than the Earth. Atoms forged in stars that burned and died before our solar system was born. Atoms that have been bacteria and ancient ocean creatures and extinct animals and soil and water before they were human. In a galaxy without stars, this journey ends. Not for the atoms already in circulation. They would persist on frozen worlds, in cold gas clouds, in stellar remnants. Matter is not destroyed by the disappearance of stars. But the forge would be cold. The process of building new complexity from simple elements would have lost its primary driver, the universe's great experiment in chemical complexity, the one that eventually produced life on at least one planet, and perhaps on many others, would have reached its ceiling. There is something almost grief-like in this recognition, even in the context of a thought experiment. The story of matter in the universe is, in its deepest sense, a story about stars. Stars are where simple becomes complex, where uniform becomes varied, where hydrogen and helium, the only products of the Big Bang, become an entire periodic table of elements, each one with unique properties, each one capable of forming unique bonds and structures and compounds. The universe spent 13 billion years building that complexity, one stellar generation at a time. To imagine it stopping is to appreciate, with unusual vividness, just how precious the ongoing process really is. Not everything would be lost. Stars do not disappear cleanly when they die under normal circumstances. They leave remnants, dense, exotic objects that persist long after the fusion has stopped. And in our hypothetical, these remnants would presumably survive the event. The question of exactly what our hypothetical entails, whether the stars simply vanished or whether they all died simultaneously in some physically consistent way, determines what they leave behind. But let's say that the remnants survive, because they are worth understanding. White dwarfs are the most common stellar remnant. They are the dense cores left behind when stars like the Sun run out of fuel and shed their outer layers. A white dwarf is roughly the mass of the Sun compressed into a volume roughly the size of Earth. Extraordinarily dense, but not as extreme as what comes next. White dwarfs are not powered by fusion. They are simply hot objects slowly radiating away heat accumulated during the star's lifetime. They shine faintly in comparison to stars, for billions of years before eventually cooling to become black dwarfs, cold and dark. No black dwarfs are believed to exist yet in the current universe, because the time required to cool a white dwarf exceeds the current age of the universe. In a galaxy without stars, the white dwarfs would be the primary sources of light initially. Their light is dim, but there are estimated to be hundreds of billions of them in the Milky Way, accumulated over the galaxy's history. In the immediate aftermath of the stellar disappearance, the galaxy would not be completely dark. It would be faintly, dimly lit by the glow of billions of cooling white dwarfs. But white dwarfs cool. Over millions of years, their light would fade. Over billions of years, they would become cold, dark objects, essentially large, Earth-sized diamonds of crystallized carbon, drifting silently through the dark galaxy. Neutron stars are more extreme. They are the collapsed of massive stars, objects containing more than the mass of the Sun compressed into a sphere about 20 kilometers across. The density is almost incomprehensible. A teaspoon of neutron star material would weigh billions of tons. Neutron stars do not rely on fusion. They are held up against further collapse by the pressure of neutrons packed as tightly as physics allows. Many neutron stars are also pulsars. They spin rapidly and emit beams of electromagnetic radiation from their magnetic poles. As the neutron star spins, these beams sweep through space like lighthouse beams. From a distance, the pulsar appears to flash on and off with extraordinary regularity. The most stable pulsars keep time more accurately than any atomic clock on Earth. In a dark galaxy, pulsars would be among the last regular signals. Precise, rhythmic, emerging from objects that require no fuel, no ongoing nuclear reactions. They would flash for tens of millions of years. Not forever, because the neutron star gradually loses energy through its rotation and its beam, slowing down and eventually going quiet. But for a long time after the galaxy went dark, pulsars would still be counting time, sending their signals into the void. And then there are black holes. Not just the supermassive one at the galactic center, but the many stellar mass black holes distributed throughout the galaxy, each one the remnant of a massive star that ended its life in a supernova explosion. These black holes are invisible in isolation, but they persist essentially forever. They contribute their gravity to the dark galaxy. They occasionally capture a drifting planet or a cloud of gas. They are patient in a way that nothing else in the universe matches. A galaxy without stars would have all of these. The cooling white dwarfs, the spinning pulsars, the silent black holes, as the primary objects in an otherwise largely empty space. It would be a galaxy of remnants, a galaxy of afterthoughts. It would be, in a strange way, like looking at civilization long after it had ended. The ruins still there, the original structure still faintly recognizable, but the living activity gone. Perhaps the most profound thing about a starless galaxy is the direction of its thermodynamic evolution. Everything would be cooling, not just as the planets and the gas clouds. Everything, the white dwarfs, cooling over billions of years toward darkness. The neutron stars, losing energy through their rotation and radiation. The gas clouds slowly radiating their remaining heat into the void. Even the dark matter, which does not interact thermodynamically in the usual sense, would participate in the gravitational rearrangement of a cooling galaxy as the structures it defined gradually changed under the influence of whatever mass remained. The universe itself has a thermodynamic future that is often called the heat death, the point at which every accessible gradient of energy has been exhausted, when nothing anywhere in the universe has any energy differential to exploit, and the cosmos reaches a state of maximum entropy. Perfectly uniform, perfectly cold, perfectly still. This future is estimated to be impossibly far in the future. More than 10 to the power of 100 years from now, a number that makes the current age of the universe seem like the first tick of the first second. It is not a near-term concern in any meaningful sense. But a galaxy without stars would be a galaxy that had skipped ahead. Not all the way to heat death, but toward it. A galaxy that had surrendered its primary energy source and begun the long cooling that is, in a cosmic sense, the destiny of all matter. What that process looks like over millions and billions of years is extraordinary in its strangeness. The gradual silencing of the white dwarfs, the slowing of the pulsars, the occasional flare of a black hole consuming a drifting planet, the slow redistribution of gas clouds, pulled by gravity into new configurations, occasionally dense enough to flirt with collapse, but with no stars to trigger them, never quite collapsing. The timescales involved are so extreme that they almost lose meaning. But they are real. The physics would continue. The galaxy would continue to evolve, just without the light and heat and chemical complexity that made it, for 13 billion years, a place where extraordinary things could happen. We have traced the first great wave of consequences: the physical, the chemical, the thermodynamic. But there is another dimension to this story: the question of meaning, the question of what it would mean to know that the stars were gone, the question of what, if anything, would remain to notice, to wonder, to ask questions about the darkness. That story, perhaps the strangest part of all, waits in what comes next. Step back from all the physics. Step back from the thermodynamics and the nucleosynthesis and the orbital mechanics. Think about what it would mean, simply as a human being, to look up. For all of recorded human history, for all of the hundreds of thousands of years before recorded history too, there have been stars in the sky. The stars have been the constant backdrop against which every human life has played out. Every civilization that ever existed was born under stars, lived under stars, and tried to make sense of the world, in part by reading and mapping and telling stories about the stars. The stars were there when the first fire was lit, when the first word was spoken, when the first painting was made on a cave wall, when the first city was built, when the first ship crossed the ocean, when the first vaccine was discovered, when the first satellite was launched. The stars were there for all of it, unconcerned, burning with the same steady patience they had maintained for billions of years before any human eye existed to look at them. They provided constancy in a world of change, navigation in a world of confusion, a sense of scale in a world that could feel overwhelmingly small, a reminder that the universe was vast and strange and full of things that defied easy understanding. To imagine them gone is not just a physics problem. It is an imaginative exercise in understanding what it would mean to lose the oldest constant in the human experience, the one thing that has been there, night after night, for every human who ever lived. The stars do not care about us. They never did. They are nuclear reactions happening at distances so extreme, they are essentially irrelevant to our daily lives. And yet they are woven into our imagination, our mythology, our science, our sense of place in the universe, so deeply that trying to imagine the sky without them is like trying to imagine a world without time. the question that survives. Before we follow the galaxy into its long future, we need to sit with something uncomfortable, something that the physics alone does not answer. If the stars of the Milky Way disappeared, if this impossible event happened in our lifetime, or even 1,000 years from now, there would be something in this galaxy capable of understanding what had occurred, something capable of measuring the loss, of tracing the consequences, of asking what came next. There would be us, and that changes the nature of the question entirely. A galaxy losing its stars is, in purely physical terms, a thermodynamic event. Energy sources disappear, systems cool, orbits dissolve. It is not a tragedy in any cosmic sense, because the cosmos does not recognize tragedy. The universe has no preference for brightness over darkness, for complexity over simplicity, for life over lifelessness. These are human values, applied to a universe that has never heard of them, but we are here. And for us, the disappearance of every star would not simply be a physical event. It would be an existential one. Imagine the first days. 8 minutes after the sun vanishes, the light stops. The sky, which was blue a moment ago, goes black instantly, not slowly, not with any warning. One moment, daylight. The next, the kind of darkness that human eyes, evolved for a sunlit world, have never had to navigate. The plants, mid-photosynthesis, would find their energy source cut. The temperature would begin its steady fall. And somewhere on the surface of this suddenly cold and dark world, human beings would look up at a sky still full of stars. The other stars, their light still arriving. And they would begin to understand what had happened. The first question any civilization would ask is, why? Not a scientific question exactly, a human one. An instinctive reaching for meaning in the face of something that seems to have none. And here is the profound thing. There may not be an answer. Our hypothetical posits an event that has no physical explanation. Stars simply ceasing to exist is not something any known process allows for. So a civilization confronting it would be confronting something unprecedented. A universe behaving in a way that its laws do not permit. That kind of confrontation does not happen on the scale of individual human experience. It has never happened in recorded history, but it is worth imagining, because it forces a question that the universe normally keeps well hidden. What do rational minds do when the universe stops making sense? Let us assume for a moment that humanity had some warning, that we detected some forerunner of the event, some anomaly in the sun's behavior, some inexplicable pattern, and had time, perhaps decades, to prepare. What would preparation look like? The physics of survival in a sunless solar system is brutal in its clarity. Within a year of losing the sun, surface temperatures on Earth would be unsurvivable for most life. Within a decade, the oceans would begin to freeze. Within a few centuries, the atmosphere itself would begin to condense. There is, however, a resource that does not depend on the sun: geothermal energy. The Earth's core is hot, extremely hot. Temperatures at the boundary between the outer core and the lower mantle exceed 3,700 degrees Celsius. This heat has been radiating outward through the rock of the Earth's interior for 4.5 billion years, and it will continue doing so for billions more. It does not require the sun. It does not require fusion. It is the residual heat of planetary formation and the ongoing decay of radioactive isotopes, uranium, thorium, potassium, distributed through the deep rock. Geothermal energy is already used by human civilization. Iceland runs a significant portion of its energy grid on it. Other regions tap geothermal heat for electricity and warmth. But in a world without a sun, geothermal energy would not be a supplement. It would be the only option. The engineering challenge would be staggering. Geothermal power is not uniformly available. It is concentrated near tectonic boundaries, near volcanic regions, near places where the crust is thin, and the heat from below can be accessed relatively easily. These regions would become the most valuable real estate on the planet, not for their scenery or their resources, but for their heat. A civilization could theoretically build underground habitats near geothermal hotspots, insulated environments where the heat from below was carefully managed to maintain livable temperatures, where LED lighting replaced sunlight for agriculture, where closed-loop ecosystems produced food without photosynthesis from the sun, relying instead on artificial light or on chemosynthesis, the process by which certain microbes derive energy from chemical reactions rather than light. This is not science fiction. Chemosynthetic ecosystems already exist on Earth, thriving around deep-sea hydrothermal vents in complete darkness. The organisms there, tube worms, chemosynthetic bacteria, strange communities of life found nowhere else, do not depend on the sun at all. They have never depended on the sun. They live in permanent darkness, powered by the chemistry of hot water and dissolved minerals erupting from the sea floor. If humanity had the time and the technology, a civilization could be built on these same principles. Underground, insulated from the freezing surface, powered by the Earth's interior, fed by crops grown under artificial light or by protein derived from chemosynthetic organisms. It would be a civilization transformed almost beyond recognition. But it could, in principle, persist for a while. Because there is a limit to how long geothermal energy can sustain a planet-wide civilization. The radioactive isotopes that generate much of the Earth's internal heat decay over time. That is the nature of radioactive decay. The heat production from these isotopes is already declining. It was significantly higher early in Earth's history. Over hundreds of millions of years, the heat flux from the interior would diminish. Eventually, the planet's core would cool enough to end the geological activity that makes geothermal energy accessible. Eventually, though on timescales of billions of years, even this source of warmth would run dry. Earth, freed from the sun's gravity, would not sit still. We established earlier that in the moment the sun vanishes, Earth continues moving at 30 kilometers per second in the direction it was heading. Over time, this motion carries the planet away from where the sun used to be, into the wider galaxy. This journey would take a very long time by human standards. Moving at 30 kilometers per second, Earth would travel roughly 1 billion kilometers per year. A light year is about 9.46 trillion kilometers. To travel 1 light year would take Earth approximately 9,500 years. To cross from one edge of the Milky Way to the other, 100,000 light years, would take nearly 1 billion years. These timescales are long even by geological standards. The dinosaurs went extinct about 66 million years ago. The Earth is 4.5 billion years old. Even the entire age of the Earth is less than 5 traversals of the galaxy at Earth's current speed. So the rogue Earth would not see much of the galaxy, not quickly. But it would move, slowly, persistently. It would drift away from the region where the sun had burned, into different neighborhoods of the galaxy. Regions with different densities of matter different distributions of stellar remnants, different configurations of gas clouds, and occasionally, the gravitational fields of other massive objects would deflect its path. This is worth thinking about carefully. The galaxy, even without its stars, is not empty. It still has white dwarfs, neutron stars, black holes, planetary mass objects that were ejected from their solar systems long ago, gas clouds, dark matter structures. All of these have mass, and mass creates gravity. Over millions of years, the rogue Earth would encounter the gravitational influence of other objects. Most encounters would be subtle, a slight curve in the path, a small change in speed. But some encounters might be more dramatic. A sufficiently close approach to a neutron star would generate tidal forces strong enough to deform the planet. A very close approach to a stellar mass black hole would accelerate Earth dramatically, flinging it in a new direction at a new speed. An encounter with a particularly dense gas cloud might slow the planet slightly, through the drag of interacting with the gas. The rogue Earth's path through the galaxy would not be a straight line. Over billions of years, it would be a complex, curving trajectory shaped by the gravity of everything it passed near. A path that could not be predicted from the initial conditions, because it would be too sensitive to the details of every encounter. The planet would become a wanderer, a traveler, moving through the dark galaxy in a path that no one, if anyone remained to observe, could fully trace. The surface of the rogue Earth would be, within a few thousand years, almost unrecognizable. The atmosphere would have partially collapsed. Carbon dioxide, water vapor, and other trace gases condensing onto the frozen surface as snow and ice. The remaining atmosphere would be dominated by nitrogen and, to a lesser extent, argon, gases that remain gaseous at the temperatures the planet would reach, but that provide no warmth and no weather as we know it. There would be wind, driven by temperature differences between different parts of the surface, but it would be cold wind, carrying crystals of frozen atmosphere across a landscape of ice. The oceans would be frozen, but not uniformly. The deepest ocean basins, far from the surface, would freeze last. By the time the surface ice was kilometers thick, the deep ocean floor would still be relatively warm, warmed from below by the same geothermal heat that might sustain civilization in underground habitats. Hydrothermal vents on the seafloor would continue to erupt, superheating water in the deep abyss, creating columns of hot water rising into a cold and slowly solidifying ocean above. The communities of life around those vents, if they survived the transition, would be the most important biological entities on the planet. Not because they are large or complex, but because they represent continuity, the unbroken chain of life on Earth, persisting through an event that would kill essentially everything on the surface, continuing in the dark and cold of the deep ocean floor. These vent communities are extraordinary, even in the world we know. They include organisms capable of tolerating temperatures that would kill almost any other life on Earth. They include creatures that can metabolize chemicals, hydrogen sulfide, methane, iron compounds, that are toxic to most life. They have developed over billions of years of evolution in complete darkness, metabolic strategies entirely independent of photosynthesis. Whether they could adapt fast enough to survive the transition to a world where even the deep ocean was under increasing pressure from the freezing above is an open question. But the possibility is real. The deep ocean is one of the most stable environments on Earth. Its temperature barely changes over centuries. The creatures living there are not accustomed to stability in the sunlit sense, but they are accustomed to consistency, to a world that changes very slowly. If any life on Earth were to survive the loss of the sun, it would be here, in the dark, at the bottom of a freezing sea, around the heat of the planet itself. There is something quietly remarkable about this. The organisms that began the story of life on Earth, the first self-replicating molecules, the first cells, the first metabolic pathways, are believed by many researchers to have originated in environments very similar to deep-sea hydrothermal vents. The chemistry is right. The energy gradients are right. The isolation from the surface is, in the early Earth context, a feature rather than a limitation. In a starless galaxy, the places where life might persist are the same kinds of places where life may have first begun. The deep, the dark, the geothermally warmed. The universe would be circling back to the conditions it started with. Earth is one planet. But we established earlier that the Milky Way contains hundreds of billions of planets. In our hypothetical, every one of them is now a rogue. Every one of them is drifting through the dark galaxy, and some fraction of them, perhaps a very large fraction, have interiors warm enough, geologically active enough to maintain liquid water beneath an ice shelf for millions or even billions of years. The astronomical community has been increasingly interested in the question of ocean worlds. Planets and moons where liquid water exists beneath a surface layer of ice, maintained not by proximity to a star, but by tidal heating or radioactive decay. Europa, one of Jupiter's moons, is the most famous example in our own solar system. Beneath its cracked and fractured ice surface, there is believed to be a global ocean of liquid salt water kept liquid by tidal heating, the flexing of the moon's interior by Jupiter's gravitational pull. This ocean has more liquid water than all of Earth's oceans combined, and it has never seen a single ray of sunlight. Enceladus, one of Saturn's moons, actively vents water vapor and ice particles from its south pole, material drawn up from a subsurface liquid ocean. Titan, Saturn's largest moon, has lakes and seas of liquid methane on its surface, and may have a subsurface water ocean as well. These worlds already exist without depending on the sun for their liquid environments. In a starless galaxy, they would continue exactly as before. Europa's ocean would still be liquid. Enceladus would still be venting. Titan's methane lakes would still be there, cold and strange and rich with organic chemistry. These bodies would have been freed from Jupiter and Saturn as those planets drifted away from the vanished sun. But they might remain gravitationally bound to their parent planets for a long time, continuing to receive tidal heating from the planet they orbit. The question of how long these systems remain intact, how long tidal heating persists in the absence of the sun's influence on orbital configurations, is complex, but there is a real possibility that some of these moon-planet pairs would remain bound and geologically active for hundreds of millions of years. And if that is true of Europa and Enceladus, which are in our solar system, then it is presumably true of many similar bodies throughout the galaxy. The Milky Way likely contains billions of ocean worlds. Icy planets and moons with liquid oceans beneath their surfaces, sustained by tidal or geothermal heat, completely independent of starlight. In a starless galaxy, these worlds would be the most interesting places in the universe, hidden beneath kilometers of ice, warmed from within, dark, quiet, alien, but potentially alive. There is a concept in the search for extraterrestrial intelligence called the Fermi paradox. Enrico Fermi, the physicist, supposedly asked a simple question over lunch. Given the age of the universe and the number of stars in the galaxy, where is everyone? The universe is 13.8 billion years old. The Milky Way contains over 300 billion stars. Many of those stars have planets. Some of those planets are in the right conditions for life. If life tends to emerge when the conditions are right, as it did, apparently very quickly, on Earth, then the galaxy should be teeming with life. Some of that life should have had billions of years to develop technology. And yet we see no evidence of any of it. No signals, no megastructures, no visitors, no traceable signatures of industrial civilization anywhere in the galaxy. Proposed explanations are numerous. Perhaps intelligent life is extremely rare. Perhaps the development of technology inevitably leads to self-destruction. Perhaps interstellar travel or communication is simply harder than it looks. Perhaps civilizations tend to go quiet rather than broadcast their existence. Perhaps we are simply not listening in the right way. But here is a scenario that the hypothetical we are exploring accidentally illuminates. What if galaxies routinely lose their stars? Not through a single catastrophic event. Our thought experiment is deliberately unrealistic in that regard. But through more gradual processes, the universe is believed to be undergoing a long-term decline in star formation. The rate at which new stars are being born in the Milky Way and in galaxies throughout the universe is lower now than it was billions of years ago, and it continues to decline. The cosmic star formation rate peaked roughly 10 billion years ago and has been falling ever since. At some point in the distant future, not millions but billions of years from now, the rate of new star formation will approach zero, not because all the gas is gone, but because the conditions that allow gas to collapse into stars will become increasingly rare. The galaxy will not suddenly go dark, but it will slowly dim over billions of years as the existing stars exhaust their fuel and are not replaced. The Milky Way is already past its peak of stellar activity. We live in what might be called the afternoon of the galaxy's star-forming era, the morning and midday when most of the galaxy's stars formed are already past. This long-term perspective raises the question, are we unusual in being here during a period when stars still burn? Have most civilizations that ever arose in the universe already faced a galaxy growing progressively darker, with fewer and fewer new stars as to replenish those that burned out? If the universe's story is one of gradually dimming galaxies, then perhaps the Fermi paradox has a quiet answer. Most civilizations that ever existed did not send signals into a bright and active galaxy, but into an aging one. A galaxy that was, in a very long and gradual sense, running down. We might be among the later arrivals, and the silence we hear might not be the silence of absence, but the silence of timing. Civilizations that rose and fell in a younger, brighter universe, whose signals have long since passed us by. There is one object in the Milky Way that will outlast everything else we have discussed. The supermassive black hole at the center, Sagittarius A, is not going anywhere. It is not going to cool. It is not going to decay in any conventional sense. In the absence of stars, in the absence of anything except the slow drift of dark matter and the occasional rogue planet passing close enough to be consumed, it will simply sit there. Black holes do evaporate, in theory. The physicist Stephen Hawking demonstrated mathematically that black holes should slowly lose mass through a quantum mechanical process. Pairs of virtual particles appearing at the event horizon, with one falling in and one escaping, carrying away a tiny amount of energy. This process, called Hawking radiation, causes black holes to very slowly shrink. For stellar mass black holes, this process is extraordinarily slow. They would take longer than the current age of the universe to lose a significant fraction of their mass. For a supermassive black hole like Sagittarius A, with the mass of 4 million suns, the timescale is incomprehensibly longer. The calculation yields a number that is almost impossible to write meaningfully. Approximately 10 to the power of 87 years. The current age of the universe is about 1.4 times 10 to the power of 10 years. Sagittarius A will exist for a period roughly 10 to the power of 77 times longer than the current age of the universe. Numbers like these stop meaning anything to human intuition, but they represent something important. In the far future of a dark galaxy, after the white dwarfs have cooled to black dwarfs, after the pulsars have slowed to silence, after the last rogue planet has wandered off into the wider universe, there will still be something at the center of the Milky Way, invisible, immense, patient beyond comprehension. The black hole will have outlasted everything else. All the light the Milky Way ever produced, all the stars that burned, and all the planets that formed, and all the chemistry that unfolded, and all the life that arose. All of it will be gone, and the black hole will still be there. There is something philosophically striking about this. The most destructive kind of object in the universe, the thing that ends stars and crushes matter out of existence, turns out to be the most durable. What the black hole has consumed, it keeps. What destroys, it preserves in a sense, encoded in the gravitational structure of the singularity, or perhaps, according to some theoretical ideas, eventually re-released as Hawking radiation when the black hole finally evaporates. The black hole is the last keeper of the galaxy's history, the last object that carries, in some encoded form, a record of everything that was. This is perhaps the hardest thing to hold in mind. While the Milky Way goes dark, the rest of the universe does not. Other galaxies would continue burning. Other stars would form in other nebulae light years away and entirely unaffected by anything that happened here. The cosmic web of structure that spans billions of light years. The vast filaments of matter and the enormous voids between them would continue its slow evolution, following its own dynamics and its own timescales. The Milky Way would be one dark spot in an otherwise luminous universe. From sufficiently far away, it would appear as a slight deficit in the background light of the sky. A region where the galaxy that used to be was no longer contributing its light to the larger glow. But it would not make the universe dark. It would barely register. This is humbling in a way that is difficult to articulate. We tend to think of our galaxy as central to our experience of the universe. It is the galaxy we live in. It is the context for everything we know. The Milky Way's stars are our stars. Its structure is our home. But to the universe at large, the Milky Way is one of hundreds of billions of galaxies, most of them containing comparable numbers of stars, all of them continuing regardless of what happens here. The loss of every star in the Milky Way would be, from a universal perspective, a local event, a neighborhood phenomenon. The universe itself would continue without noticing. This is, in its own way, one of the most profound scale comparisons available to us. We struggle to comprehend the size of the Milky Way, 100,000 light-years is already beyond meaningful imagination, but the observable universe is 93 billion light-years in diameter, and it contains an estimated 2 trillion galaxies. A number revised upward dramatically in 2016 from previous estimates. Our galaxy is one of 2 trillion. What happens to the Milky Way is, from the universe's perspective, what happens to a single cell in a human body. The body continues. It is the most hopeful question available to us in this thought experiment. And the answer is, possibly. Under certain circumstances, after an extraordinarily long time. Here is why. The gas that used to be in stars does not disappear when the stars vanish. In our hypothetical, the matter that made up 300 billion stars simply ceases to be organized in stellar form, but the atoms remain. They are presumably scattered back into space, or they simply remain as cold, dark gas wherever they happen to be at the moment the stars vanish. Over time, that gas, hydrogen and helium and heavier elements, all of it cold and slowly moving through the dark galaxy, would be subject to gravity. And gravity, given enough time, does what it has always done. It pulls things together. The gas clouds of the Milky Way, slowly drifting and gradually being compressed by their own gravity, and by the gravitational structure of the dark matter halo, would eventually reach densities high enough that new processes could begin. The key question is whether, in the absence of the feedback effects provided by stars, the radiation pressure, the stellar winds, the supernova shock waves that normal star formation relies on to regulate itself, the gas could condense into something new under the right conditions. A dense enough cloud of hydrogen and helium collapses under its own gravity and heats up as it does. The center grows hotter and denser. If the conditions are right, it reaches temperatures and pressures sufficient to ignite nuclear fusion. A new star is born. The time frames involved in this scenario are immense. The gas would have to cool and condense and organize itself without the turbulent stirring that normal stars provide. It might take hundreds of millions or even billions of years for the gas to settle into configurations dense enough for new collapse. But over the enormous timescales of a dark galaxy, that time would pass. And if it did, if, somewhere in the cold, dark Milky Way, a single cloud of gas managed to collapse and ignite, the consequences would be extraordinary. A new star, burning in an otherwise dark galaxy, pouring heat and light and ultraviolet radiation into the gas around it, potentially triggering further collapse in neighboring clouds, beginning perhaps a new cycle of star formation. The galaxy would not be dead, it would be sleeping. There is precedent for this idea in the broader universe. Some galaxies that astronomers observe have gone through phases of very low star formation, followed by sudden bursts of activity, triggered by collisions with other galaxies or by internal processes that disrupted and rearranged their gas supplies. Galaxies can be dormant. They can also reawaken. The Milky Way, given billions of years and sufficient remaining gas, might reawaken too. There is one event scheduled in the far future of the Milky Way that changes the calculations significantly. The Andromeda Galaxy is approaching. Not metaphorically, literally. The Andromeda Galaxy, the Milky Way's nearest large neighbor at 2.5 million light-years away, is moving toward us at roughly 110 kilometers per second in approximately 4.5 billion years, give or take. Andromeda and the Milky Way will begin to merge. This collision would not be like two billiard balls striking. Galaxies are mostly empty space. The stars in each galaxy are so widely separated that actual stellar collisions during a galactic merger are extraordinarily rare. Instead, the two galaxies would pass through each other. Their stars and dark matter mixing and interacting gravitationally, their gas clouds colliding and compressing and triggering enormous bursts of new star formation. Galactic mergers are among the most productive events in the universe for star formation. When two gas-rich galaxies collide, the compression of their interstellar medium generates conditions ideal for rapid, intense stellar birth. Astronomers observe galaxies in the process of merging throughout the universe, and they glow brilliantly, far more brightly than either galaxy did before, because of the enormous number of new stars forming in the compressed gas. Now, consider what this means in the context of our thought experiment. If the Milky Way had lost all its stars, but retained its gas, its cold, dark clouds of hydrogen and helium and heavier elements drifting through the dark matter halo, it would still be, gravitationally, a galaxy. The dark matter halo would remain. The gas would remain. The trajectory through space would remain. And in 4.5 billion years, Andromeda would still arrive. The merger would still happen. Andromeda's gas and the Milky Way's gas would still compress and interact. The Andromeda stars would still light up the interaction zone with their radiation and their winds. The shock waves moving through the combined gas reservoir would be dramatic, far more dramatic than in a normal merger, because the Milky Way's gas, which had been cold and undisturbed for billions of years, would be suddenly compressed and heated with enormous force. The result could be an extraordinary burst of star formation. New stars, born from the collision of two galaxies, burning in a region that had been dark for billions of years. A reawakening triggered not by any internal process, but by the arrival of a neighbor. The Milky Way, having been dark for 4 billion years, might light up again, not with the stars it lost, but with new ones, born from the collision. This is not a guaranteed outcome. It depends on how much gas remains, how the merger geometry plays out, how the various physical processes interact. But it is a possibility, grounded in real physics and real astronomical observation. Galactic mergers produce star formation. A merger with gas-rich Andromeda would produce enormous star formation, regardless of whether the Milky Way still had its own stars. The galaxy might not be permanently dead. It might simply be waiting for its neighbor. We have spent this entire journey in darkness, imagining a galaxy that has lost what makes it remarkable. And perhaps the most important thing that journey reveals is not what darkness would feel like, but what light actually means. Stars are easy to take for granted. They are always there. They have been there every night of every human life ever lived. They rise and set with a regularity that feels permanent, because on human timescales it is. The star that humans have called the Sun will continue burning for approximately another 5 billion years. By any measure that matters to us, it is eternal. But it is not eternal. It is the product of a specific chain of events, a cloud of gas that collapsed under gravity at a specific moment in the galaxy's history, igniting fusion, maintaining a balance between gravity and pressure for billions of years, and eventually, billions of years in the future, exhausting its fuel and ending. Every star in the Milky Way is like this, each one a temporary equilibrium, each one specific event in space and time, not guaranteed, not permanent, not obvious. The fact that there are 300 billion of them and that they have been burning for billions of years, and that one of them was the right distance from the right planet to allow complex chemistry and eventually life and eventually consciousness. All of this is not inevitable. It is a consequence of specific conditions that happen to align. The thought experiment of losing every star is, in its deepest sense, an exercise in recognition. Recognition that what we look at when we look at the night sky is not background, not decoration, not scenery. It is an engine. An engine that has been running for 13 billion years, building complexity out of simplicity, forging elements from hydrogen, warming worlds, driving chemistry, providing the energy that life needs to exist and evolve, and eventually look back at the sky and ask questions about what it sees. To imagine that engine stopping is to understand, with unusual clarity, what it means that it is running. There is one final dimension to what would be lost, something that is not heat or light or gravity or chemistry, but something more subtle and perhaps more profound. Stars are records. Every star in the Milky Way is a physical record of the conditions that prevailed when it formed. The composition of a star, the ratio of hydrogen to helium to heavier elements, the specific mix of carbon and oxygen and iron and other metals, tells astronomers about the environment in which that star was born. Stars formed early in the galaxy's history from relatively unprocessed hydrogen and helium have a different composition from stars formed later, from gas enriched by generations of supernova explosions. These differences are readable. They are a kind of geological record written in stellar chemistry. Similarly, the distribution of stars in the galaxy, their ages, their positions, their orbits, tells the story of the galaxy's history. The thick disk, the thin disk, the bulge, the halo. These different structural components of the Milky Way each reflect a different era and a different process in the galaxy's past. The stars of the halo, orbiting in long elliptical paths, well above and below the galactic plane, are among the oldest objects in the Milky Way. Relics of an early era before the galaxy had settled into its current flattened shape. The stars of the thin disk are younger, born more recently in the calmer, flatter structure the galaxy has today. Reading these records is how astronomers reconstruct the history of the Milky Way, not by observing that history directly, but by reading it in the stars themselves. Without stars, this archive is closed. The record is not destroyed. The atoms that made up the stars are still there, in various forms. But the organized information, the stellar compositions, the orbital patterns, the age distributions, would be scrambled. The library would not be burned. It would simply be dispersed. And in a galaxy where new stars eventually formed, if they did, those new stars would not remember the history of the old ones. They would be born from gas that had been mixed and stirred and rearranged over billions of years of darkness. They would have their own compositions, their own stories, but the history of the galaxy that burned for the previous 13 billion years would be, in the deepest sense, unreadable. The new stars would look out at a universe with no knowledge of what had come before them. They would be starting over. Here is what the physics tells us, stripped to its most essential form. The universe is approximately 13.8 billion years old. It is expected to continue for a period so much longer than this, that the current age of the universe is essentially the very beginning of the cosmic timeline, the era in which stars like our Sun exist, known to cosmologists as the stelliferous era. will last approximately 100 trillion years. After that, the last stars will burn out, and the universe will enter a long sequence of eras, defined not by burning stars, but by the slow decay of more durable objects, the degenerate era of white dwarfs and neutron stars, lasting up to 10 to the power of 40 years, the black hole era, lasting up to 10 to the power of 100 years, and then, finally, the dark era, when even the black holes have evaporated and the universe contains nothing but slowly cooling elementary particles. Against this timeline, our entire hypothetical, the loss of every star in the Milky Way, the cooling of the planets, the slow drift of the galaxy into darkness, is a very early event in a very long story. The disappearance of the Milky Way's stars would leave the universe largely unchanged. The story of the cosmos would continue in other galaxies, on other timescales, with other stars and other planets, and whatever other kinds of complexity the universe still has in store. The universe is patient. It does not need the Milky Way to continue. It does not need any particular galaxy. It does not need life, or intelligence, or the specific form of complexity that produced the question we have been exploring. But here, right now, in this brief warm window of stellar time, these things exist. And the fact that they exist, the fact that the universe has organized itself in this galaxy around these specific stars in a configuration that produced planets and oceans and life, and eventually minds capable of looking up at the night sky with wonder, is not something to underestimate. The universe has had, and will continue to have, an almost incomprehensible amount of time and space in which to arrange things. In all of that, the arrangement that produced us, and the stars we look at, and the questions we ask about them, is one specific outcome among almost infinite possible ones. It is, by any reasonable measure, remarkable. Return to the surface of the earth on a clear night far from any city. You are standing in a field, or on a hillside, or beside an ocean. The sky overhead is dark, and the stars are out. Not a handful, thousands of them. The Milky Way itself, in the right conditions, is visible as a pale band of light arching overhead, a concentration of distant suns, so numerous they blur together into what looks like a cloud. You know, now, what you are looking at. You know that each point of light is a nuclear reactor, burning hydrogen into helium, pouring energy into the space around it. You know that the light reaching your eyes from the nearest stars left those stars years ago, that what you see is a record of the past, rather than a window to the present. You know that the galaxy contains 300 billion of these objects, that your sun is one of them, that the Earth exists because of it. You know what would be missing if it were gone, not just the light, the warmth, the gravity, the chemical complexity, the navigation points, the calendar anchors, the mythological sources, the archive of the past written in stellar chemistry, the engine of biological possibility, the cosmic context within which life has always evolved and wandered and reached outward. You know that the stars are not permanent, that they will burn out, eventually, each one, and that the galaxy itself is in a long, slow decline toward a future in which stellar birth becomes rarer. You know that the sun will expand and cool, and eventually leave behind a faint white dwarf, and that by then the Earth will be gone. And you know, perhaps most importantly, that none of this changes what the moment is. Standing in that field, looking up, you are part of a long chain of living things that have looked at these stars. You are the universe becoming aware of itself. An arrangement of atoms that were forged in stellar cores, standing on a planet warmed by a star, looking out at billions of other stars, and understanding, in some small measure, what they are. The stars do not know you are there. They cannot. But you know they are there, and in that asymmetry, the universe observed, the universe aware of itself through the instruments of life and mind. There is something that the physics alone cannot quite capture. There is a reason to look up. There has always been a reason to look up. The stars have been patient. They have been burning for billions of years without anyone to notice. And now, in this brief window of cosmic time, something on one of their planets looks up and wonders. That seems worth mentioning. It seems, in the quiet of a clear night, worth everything. What would happen if the Milky Way suddenly lost every star? The sun's light would stop arriving at Earth after 8 minutes. The temperature would begin to fall. The orbits of every planet in every solar system would dissolve. And billions of worlds would begin to drift through the dark galaxy. The great forges of stellar nucleosynthesis would go cold. The ionized gas clouds would neutralize and fade. The cosmic rays would find no heliospheric shields to deflect them. The pulsars would slow to silence. The white dwarfs would cool to blackness. The gas clouds would drift, cold and dark, through the gravitational skeleton of dark matter that no longer had stars to illuminate it. And in the deep places, beneath the ice of frozen planets, around the geothermal vents of worlds still warm from within, life might persist, quietly, in the dark, for a very long time. And eventually, over billions of years, the gas would cool and condense. And if the conditions aligned, if the densities reached the threshold, if the temperatures and pressures were right, something might collapse and ignite. A single point of light in a dark galaxy, and then another, and then another. Because the galaxy would not have lost its matter. It would only have lost its fire. Fire, given enough fuel and enough time, has a way of returning. The Milky Way might one day burn again. But the most important thing, the thing that gives all of this its weight and its meaning, is not what would happen in the dark future. It is what is happening right now. Right now, 300 billion stars are burning in this galaxy. One of them is warming a planet. That planet has oceans and an atmosphere and billions of years of accumulated biological complexity and minds that look up at the night sky and ask questions. Right now is the era of stars. Right now is when the forge is hot. And the night sky, with all its ancient patient light, is the evidence. The universe is not just a place we live in. It is a process we are part of, made from the same elements, running on the same energy, following the same physics as everything that burns and drifts and wanders in the dark between the stars. The Milky Way is not a backdrop. It is the story, and the story is still going. There is a branch of physics that deals with information, not in the colloquial sense, but in the rigorous thermodynamic sense. Information is, in this framework, the specific arrangement of matter and energy. Every configuration of atoms, every position of every particle, every quantum state of every field. All of it constitutes information. And the laws of physics, at their most fundamental level, are believed to conserve it. Information, the theory says, cannot be destroyed. This is a deeply contested idea in the context of black holes, and it gives rise to one of the most famous unsolved problems in physics, the black hole information paradox. but it has a broader relevance to what we have been discussing. If information is conserved, then the disappearance of every star in the Milky Way would not, strictly speaking, destroy the information encoded in those stars. That information would have to go somewhere. In the extreme hypothetical, where stars simply blink out of existence, this becomes a physics problem of the most fundamental kind, because conservation of information is closely linked to conservation of energy and the unitarity of quantum mechanics. The stars cannot simply vanish without that violation being deeply problematic for the laws of physics themselves. But let us set aside the purely hypothetical physics and think about what information loss means more practically. When a book burns, the information in the book is not destroyed in the strict physical sense. The atoms rearrange. But in principle, a sufficiently detailed knowledge of the final state of the ash and smoke and gases could allow you to reconstruct what was on the page. In practice, this is impossible. The information is scrambled beyond any practical recovery. For all functional purposes, it is lost. The same is true of the Milky Way's history, encoded in its stars. The positions of the stars, their compositions, their ages, the relationships between them. Which stars orbited, near which star systems had been enriched by the supernovae of their neighbors, which stars had shaped the chemistry of which planetary systems. All of this is a record, imperfect, but readable by astronomers, of the galaxy's 13 billion-year history. Without the stars, this record disperses. Not into nothing, the atoms remain, but into a form that is, for any practical purpose, unreadable. The library is disassembled, the pages are scattered, the ink diluted into a vast cold ocean of mixed gas. What remains is the raw material, not the record. A new civilization forming in the Milky Way 100 billion years from now. In the hypothetical scenario where new stars eventually reignite, would find themselves in a galaxy with no accessible memory. They would not know that 300 billion stars had once burned here. They would not know that planets had formed, and life had arisen, and minds had looked up and wondered. The evidence would be there, in principle, encoded in the quantum states of every atom. But it would be unreadable, lost, in every meaningful sense, to time. This is perhaps the most poignant consequence of all. Not the freezing of the planets, not the cooling of the oceans, not even the extinction of life, but the forgetting, the loss of the record, the erasure of the story. Something else disappears with the stars, something so obvious that it is easy to overlook. The concept of seasons, not just Earth seasons, the seasonal cycles of every planet around every star in the galaxy. Seasons exist because planets orbit stars at angles, exposing different hemispheres to different amounts of light at different times of year. Without stars, there are no seasons. No annual cycle, no summer or winter, no migratory patterns triggered by seasonal change, no agricultural cycles, no solstice or equinox. More broadly, no concept of a year at all. The year, as a unit of time, is defined by a planet's orbit around a star. It is not an arbitrary unit. It is a physical cycle rooted in the relationship between a planet and its host star. Remove the star, end the orbit, and the year as a concept has no physical foundation. This connects to something deeper about how we understand time. Human beings, and presumably any intelligent creatures that might have evolved elsewhere, calibrate their sense of duration against natural cycles. The day, one rotation of the planet, the month, approximately one orbit of the Moon, the year, one orbit of the planet around the star. These are not just convenient units. They are the natural rhythms of the world, the cycles that life evolved in, the background pattern against which change becomes perceptible. In a starless galaxy, on a rogue planet, there is no rotation that matters, or rather, the rotation continues but has no significance, because there is nothing to rotate relative to in any meaningful sense. There is no orbit. There is no moon if the moon has drifted away. There is no year. Time would continue, seconds, minutes, hours. The rhythms of physics would go on. But the larger cycles, the ones that gave structure to biological life and human civilization, would simply not exist. Time would become, in a strange way, featureless. A river without banks. We have been careful throughout this journey not to anthropomorphize the universe. The universe does not care about the Milky Way's stars. It does not grieve their loss. It does not celebrate their existence. The cosmos has no preference for brightness, but we are allowed to. The night sky has shaped human culture in ways so deep and so old that most people no longer notice them. Constellation. The constellations, those arbitrary patterns that different cultures have projected onto the same stars, are evidence of how deeply human minds need to make meaning of what they see overhead. Every culture in human history has looked up and seen stories. Orion the hunter, Ursa Major the bear, the Southern Cross, the Pleiades, which appear in the myths of cultures, separated by thousands of miles and thousands of years, on every inhabited continent on Earth. The same stars, different stories, but always stories. This is not a coincidence. It is an expression of something fundamental about how minds work. We see patterns, we make narratives, we impose meaning on the universe because meaning is what minds produce. It is what minds are for, in the sense that eyes are for seeing and lungs are for breathing. The stars gave us something to make meaning of at the largest possible scale. They gave us a canvas for the biggest questions. Where did we come from? What are we? Are we alone? What happens after we die? Where does everything go? These questions did not begin with telescopes or physics. They began with ordinary people looking up at an extraordinary sky and feeling, in the presence of something so vast and ancient and incomprehensible, the particular kind of smallness that leads not to despair, but to wonder. To lose the stars would be to lose the canvas. Not the questions. The questions are internal. They would persist in any mind capable of asking them. But the external prompt, the thing that triggered the questions in the first place, the sky that said, without words, that the universe was bigger than any single life, older than any civilization, stranger than any imagination. There is a particular silence that astronomers know well. Not the silence of an empty room, or the silence of a forest at night, but the silence of the radio spectrum, pointed at a distant star. When radio telescopes scan the sky for signals from extraterrestrial civilizations, the project known as SETI, the search for extraterrestrial intelligence. What they hear, most of the time, is static, the natural radio noise of the universe. Pulsars, quasars, the cosmic microwave background, the emission lines of hydrogen and other molecules in interstellar space. But no clear signal, no pattern that could only be explained by intelligence. The silence, as we noted earlier, is one of the great puzzles of modern astronomy. But consider what the silence would sound like in a galaxy without stars. There would be no radio emission from stellar winds, No X-ray emission from stellar coronae, no ultraviolet from hot young stars, no infrared from stellar nurseries, no optical light from main sequence stars. The galaxy's electromagnetic spectrum would be dramatically impoverished. The natural noise would drop to nearly nothing. Just the cosmic microwave background, the occasional faint emission from gas clouds, the radio beams of the remaining pulsars sweeping through the dark. And in that silence, any signal from anywhere would be extraordinary. If there were any civilization anywhere in the galaxy, somehow surviving the darkness, in an underground habitat, on a geothermally active world, anywhere at all, their communications would stand out against the quiet like a lighthouse beam on a perfectly dark night. The galaxy, having lost all the electromagnetic noise of stellar activity, would be the most radio quiet it had ever been. Paradoxically, the easiest time to find a signal in the Milky Way might be when the Milky Way had no stars left to produce interference. Not that there would be anyone to look, but the thought is worth holding. Let us return, one final time, to the idea of what could be seen in a starless galaxy in the first decades after the sun's light stops arriving at Earth. Assuming any observer survived, the night sky would initially still be full of stars. The Milky Way's stars, their light still in transit, would continue illuminating the sky for years, decades, millennia, depending on their distance. But there would be something else. Other galaxies. The Andromeda Galaxy, 2.5 million light-years away, would continue appearing in the night sky for 2.5 million years after our galaxy's stars went dark. It would be faint. It is already one of the most distant objects visible to the naked eye, but it would be there. A smudge of light in an otherwise darkening sky. And beyond Andromeda, other members of the local group. The Triangulum Galaxy, the many satellite galaxies orbiting the Milky Way and Andromeda. And beyond those, the galaxies of the Virgo cluster, tens of millions of light-years away, their light still arriving. The universe outside the Milky Way would continue shining. And from the surface of a rogue planet, if the atmosphere had not yet fully collapsed, if there was still a surface from which to observe, you would be able to see them, faint and distant and unreachable, but luminous, proof that the extinction of stars in one galaxy was not the extinction of stars in all galaxies, proof that the universe was still burning elsewhere, in other forms, around other planets. Proof that the story was still going. It would be, perhaps, the most important thing a surviving observer could know. The lights were still on, not here, but somewhere. That knowledge, if anyone were there to hold it, would be worth more than almost anything else that remained. Imagine a clear night, somewhere on Earth, before any of this happens. The temperature is comfortable, the air is still. The city glow is far enough away that the sky is dark, genuinely dark, and the stars are visible in their full number. The Milky Way arches overhead, a river of light made of light years and billions of years and more nuclear reactions than any mind can hold. You know what you are looking at. You know the stars are engines. You know the light is old. You know the sun is temporary, and the galaxy is aging, and the universe is larger than comprehension can follow. You know all of this now, in a way that you perhaps did not before, and still, maybe because of it, the sky is beautiful. Not beautiful in spite of being physics. Beautiful because it is physics. Beautiful because the universe is organized the way it is, in this particular corner of existence, in this particular moment of cosmic time, so that a planet exists in the warmth of a star, and life arose on that planet, and that life eventually produced minds, and those minds looked up and could not look away. The stars have been there for longer than the Earth has existed. They will continue burning long after any individual human life has ended. They are, in the deepest sense, indifferent to us, but we are not indifferent to them. And in this universe, in this galaxy, in this moment, that seems to matter. The stars are still burning. The night is still clear. There is still time to look up. There is always time to look up.